started here. Glad to see a very full room today. Good job on Labor Day. Nice day outside. First of all, I'm going to make one note here. So as you can see down here, there's a camera videotaping me while I'm giving lab lecture. The reason for that is to have this available as a resource for you. The video, now you can see the camera on top. It's not like a super high-powered, wonderful camera. It's a camera that catches most of what I write on the board and my audio, but it shouldn't be a substitute for you being in the seat, so I'd like to see this every week, everybody in the seats. But if there is a time that you're going to miss lab lecture, because this is the only time that lab lecture will be given, the video will be posted on Moodle. And so the Moodle course that I use is there is a Moodle course that is for all 7 lab sections. Each week this video will be posted. It's through YouTube, so the link will be posted, okay? I make the promise that we will videotape each week. I don't make the promise about how well the technology will work beyond what we do each week. So there is weeks that there could be glitches too. If you know you're going to miss, what I recommend is count on watching the video. Hopefully it's up there and available. But also I'd have someone take notes for you too to make sure that if there is anything you can't hear very well, you can't see very well, or the video had trouble getting loaded to Moodle or to YouTube, that you do have what you need available to you, okay? Each week I'm going to put kind of the schedule for the week or schedule for the next couple weeks up here on the board, and we'll go through those announcements. And then over on the other board, I'll kind of put a little bit of an outline of what we're going to talk about in lab lecture. So this week in lab, we're going to finish the parts 2 and 3 of experiment 1, all right? So we'll talk through here in a little bit all those parts, but we will be completing parts 2 and 3. Remember that your homework for the last week has been, first of all, your pre-lab that we gave to you last week in some form needs to be in your lab notebook, whether that is you handwrite what we gave you into your notebook, or you took the physical copy that we gave you and you cut and pasted that into your notebook. So go by the guidelines that your lab prof gave you as to how they want them in the notebook, but make sure your pre-lab is in there. The other thing that was homework was we didn't give you all of the flow charts that you needed. We only gave what you needed for last week's lab, and you need to include the flow charts for part 2 and part 3 in that pre-lab. Okay, so before you come to lab, make sure your pre-lab is in there. And every week before you start a new experiment, make sure your pre-lab is in your notebook before you come to lab, because they'll be checked right at the start of lab, and you can't start the experiment unless you have your pre-lab in there. Otherwise, you're going to have to, while everyone else is starting the experiment, if you don't have it ready, you'll have to get the pre-lab into your notebook, all right? This week we will have our first quiz, so make sure that you have looked over the material for that. Anything covered in lab last week in our very lengthy lab lectures that won't happen again in lab, or anything that I covered this week, anything in the intro or experiment 1 in your lab manual is fair game. And I'll say for the quizzes, any safety information is always fair game for any quiz, okay? So don't just try and learn it for this quiz. We want to make sure that you always are ready to go with the safety information. Always make sure you bring a calculator to lab for the quiz, but for just making calculations in lab, and you can't use a cell phone on the quiz, so make sure you've got a calculator in lab with you every week. Next week we will be doing experiment 2 in lab. I will tell you this is the one experiment that you'll do this year that you won't need a pre-lab in your notebook. So you don't need a pre-lab in your notebook for experiment 2, but I'll talk to you in lab lecture next week about what preparation you do need for experiment 2. And then some lab sections mentioned this, some didn't. So in addition to our scheduled lab times, which we'll look at the syllabus here in a minute, we have open lab hours Monday, Wednesday, and Friday in the labs from 9:30 a.m. to 3:30 p.m., okay? On Fridays, they potentially could end earlier if we have seminars that are going to start earlier than 4 o'clock. So we have it ending at 3:30 so that everything's closed in time for the seminar at 4 o'clock. If we have a seminar that is earlier than 4 o'clock during the semester, then we will end a half hour before that seminar. So I know there's one date in October where that's going to happen. We have a 3 o'clock seminar. We'll close at 2:30 on that Friday, okay? But these are the general times. If there was ever a time that a lab prof couldn't be available as emergency contact, we would have to close open lab during that time as well, okay? But rules for open lab, first of all, dress code for open lab, same as lab. So safety glasses on, basically neck through feet covered, no sandals, no flip-flops, things like that, and lab shoes that actually cover your entire foot, pants, short sleeve shirts on. Make sure that if you're doing a melting point, collecting a weight, or in a couple weeks you'll know what collecting an IR spectrum means. You don't need to bring a buddy with you to open lab, but make sure as you're going into open lab, you're letting the stockroom attendant, there's going to be someone sitting in the stockroom, let them know what you're doing in lab so they have an idea of what's going on, okay? And then make sure when you go to leave, you have that stockroom attendant, unless there happens to be an instructor walking through lab as well, sign your notebook just like your TA or instructor signed your notebook in lab this week, okay? If you need to do something more than a melting point, collect a weight, collect an IR spectrum, then you need to let your lab prof know that you will be going to open lab and when that will be, and you also need to have a person in the lab with you, okay? So, and that person doesn't have to be another organic student, it just has to be someone properly dressed. They're your emergency person, so they're the person that's going to go get help if an emergency arises. So you can borrow safety glasses for them from the stockroom, but they do need to be properly dressed, and they just need to sit in the lab with you in case an emergency arises, okay? Questions at all with that? Okay, and the schedule for the days is posted in orange on each lab door. Monday, Wednesday, and Friday are each interior lab door by the stockroom. Monday, Wednesday, and Friday, the lab doors that will be open will be the ones just by the stockroom, so that the stockroom person can see the people coming in and out as well. Okay. All right, now let's look at the syllabus really quick that everybody should have received in lab last week, and then I have now also posted it on the Moodle site for all of the lab sections. So a couple things. First of all, we've got all the lab sections on there. Make sure that you are here each week, Monday, for lab lecture at 4 o'clock. You will, like this week in lab, you'll be having a quiz each week. So material for the quiz, anything covered in lab lecture is always fair game for material from the quiz, okay? And like I said, we're not going to rehash what I cover in lab lecture. We may show you a technique or show you how to set something up or do something like that, but we're not going to completely give the same lab lecture again, okay? So this is the one time that it is given. So in order to be prepared for lab, in order to be prepared for the quiz, as well as we have a final exam that we will all take here in this room together, is the Monday of exam week, the 14th, at 12:30, so 12:30 to 2:30 is the final exam for this course, which corresponds to the Monday, Wednesday, Friday classes at 4 o'clock. Anything covered in lab lecture is also fair game for that exam, okay? So just make sure that you are up to speed with what is covered in lab lecture, all right? And the rest of the syllabus I'm not going to go through because we all covered that last week in lab itself. What I do want to show you, kind of rehash just a little bit of where we're at here, kind of minus this part. So last week in lab, you had your neutral compound, your organic acid compound. We added base to the acid, we deprotonated the acid and made it water soluble, okay? Then we added hexane to dissolve your organic neutral compound because it's all carbon and hydrogen. Just like hexane, it went well into the hexane, all right? Then you use your subfunnel to do acid-base extraction. You separated the two layers, and then we needed to protonate the aqueous layer to get our organic acid back out. You did a filtration, and you got your organic acid out as well as the filtrate, okay? So in the end, you ended up with your solid carboxylic acid and your neutral compound that's in hexane that we need to get rid of the hexane this week, all right? So we're going to start there for talking about what you're going to do next week, and then, or what we're going to do in lab this week, and then we'll talk about the characterization you're going to use for your compounds as well, okay? So the first thing we're going to talk about is recrystallization. We're going to use that for both the acid compound and the neutral compound. And actually, before I go into that, a couple of things I do want to mention. Make sure both open lab and your lab, which you guys did a fine job last week, but make sure you always clean up your area. Also, be careful because this is the time now we're all going to end up with 2 white solids. Make sure the solids get back into your drawer because if everybody leaves out their white solid unlabeled, I'm not going to know who they go to. They may end up in the waste container. So make sure your white solids all go back in your drawer when you're collecting melting points, so on and so forth. Just keep your lab area neat and tidy. And then the other thing to be careful of is make sure you understand what goes in the organic waste. No water goes in the organic waste, only organic waste goes in the organic waste. So if you have questions about that, make sure you ask, but always make sure you leave either open lab or regular lab, your hood neat and tidy, the other spaces you worked in neat and tidy, dry. One thing I would say is once you wipe out the hood, dry out the hood, things like that, so they're ready for the next lab section, okay? Okay, so with recrystallization, to recrystallize a solid, which is a purification technique, so we're taking a not so pure solid and we're going to do something to it to clean it up and hopefully get that solid back, but clean, okay? And it involves dissolving it in a hot solid, cooling it back down, it crashing out, and then we filter our solid off, okay? And hopefully leave the impurities in the filtrate. Well, big part of the recrystallization is you need how to choose a good solvent, which we've already done that for you, but you need to understand what goes into choosing a good recrystallization solvent. So we'll talk about that, and then we'll talk about the actual process itself, what we're hoping to achieve, okay? Recrystallization. So the first thing we want is we're going to dissolve the solid in the solvent, but we don't want it to react at all. Okay, so you want the same solid to come back out, but it to be pure. So you don't want the solid, which is your product. You want no reaction with the solvent. Okay. And I'm talking about recrystallization solvent. Then what you want to do too is also make sure that what you're using, you don't want to use we want to pick solvents that are fairly innocuous. We don't want to use like something super toxic, has to be handled with a lot of care. We're going to have to heat the solid up. We don't want something that's going to have a lot of health hazards involved, okay? So the solvent or solvent vapors, because we're going to produce vapors, should not pose a significant health hazard. And then number 3, what we want is that solid to be really soluble in hot solvent, so it dissolves, but we don't want it to be very soluble in that solvent at room temperature at 0 degrees, okay? Now the other thing is, we don't want the impurities to be changing solubility, okay? So we don't want them to become really soluble, and then when you pull it down to become really insoluble, because then when we crash things out and filter things, we're not going to change the purity of that solid. It's still going to have those impurities in it, okay? So the impurities do not change solubility with the temp of the solid. And you're still going to have a little bit of solubility of the solid and the impurities in cold solvent, okay? So you're never going to get where you have the solid is really super soluble in hot solvent, not soluble at all in cold solvent. So what this is telling you as far as yield, from recrystallization, most likely you're never going to get exactly 100% yield, okay? Because you're always going to lose a little bit that was soluble in the solvent once you filter it. Now, what I want to do is we're going to look at an example. I'm going to learn to push harder here. Look at an example of what this means as far as numbers, okay? So if we have an example here where we've got cold solvent and the solubility of things, and we've got hot solvent, how do their solubilities vary? So we've got our solid, our product that we want to recrystallize. In cold solvent, we don't want to see a lot of solubility. So maybe something like 0.1 grams per 100 grams of solvent. There'll be a little bit of solubility, but not a lot. What we want to see is in the hot solvent, say, like 10 grams per 100 grams of solvent as far as solubility. So we want it really increasing in that hot solvent, okay? And this is the key to why when you recrystallize, you want to keep that solvent hot. You don't want to ever let it be cooling down as you're still trying to get things to dissolve. The impurities, hopefully we don't have a lot of impurities. So, but the impurities that we have, say we've got a 0.1 gram per 100 grams of solvent, solubility in cold solvent, we want to see a similar effect in hot solvent, okay? So in the end, we want to make sure that we've got the solid that we're interested in getting out as pure form, well dissolved, and not very much of the impurities dissolved in that solvent at all, okay? And like I said earlier, you're still going to have some cold product dissolved in the solvent at cold, or some product dissolved in the solvent at cold temperatures, so you are going to lose a little bit in the filtrate. The other thing you've got to be careful of is because of the solubilities, what we don't want to do is use a ton of hot solvent to get it to dissolve, because when it goes to cool down, it may not crash out because it will stay a little bit soluble in some solvent, okay? So another key to recrystallization is you always want to use a minimal amount of hot solvent to dissolve the solid, okay, or the product. So like for the carboxylic acid in your lab manual, it tells you how much ethanol to heat up. You're going to be starting with ethanol for your recrystallization, how much ethanol to heat up, and then how much you should have added to your solid. It shouldn't be more than 10 milliliters of solvent. If you end up adding more than that, then you want to make sure that you're talking to your lab prof before you add any more than about 10 milliliters, because that's a lot for what you're going to have to recrystallize, okay? So really keep in mind, once you've added enough hot solvent for it to dissolve, you're done, okay? You don't want to add any more than that. Now another thing that your lab manual talks about is the hot filtration, okay? Especially for the carboxylic acid. I'm going to show you the setup for that, but then what I want to caution you is be careful not to use this unless you're absolutely certain that you need to, okay? So if you think you need to use a hot filtration for your carboxylic acid, you're going to filter it after you've added the ethanol, but before you've added the water. So you've gotten to a point where you can't get anything else to dissolve with hot ethanol. You're going to do this hot filtration, and then you'll go on and add the water to it and get everything to crash out, or get the product to crash out. I caution you to be careful with this though. Make sure that you actually do need it, and it's not just a matter of you just need a little more heat or a little more solvent to get your solid to dissolve, okay? Because what could happen is if you don't need it and you go through the process, you end up getting solid dissolving on the filter paper, or crashing out on the filter paper, on the funnel, crashing out all the way through, and then you've got this mess that you've got to get redissolved again, okay? So to do a hot filtration, you're going to have your hot plate on, not very, very hot, but like 1 or 2, or the older hot plates low or so. Whatever setting you use to get your ethanol hot, that's what you want for the hot plate. You're going to put an Erlenmeyer flask on there, and you're going to have just a little bit of solvent in the bottom of your Erlenmeyer flask to help keep everything here hot and keep the vapors hot, okay? Then you're going to have a funnel, and you're going to use fluted filter paper. So if you have to do a hot filtration, we'll show you how to flute filter paper, okay? Then you're going to very carefully handle, this shows a towel, but you guys should have hot pads in your drawers. Handle the flask and pour the hot flask that you had everything dissolving in that flask through the filter paper. And ideally, if we've kept this all hot, all of the solid will stay dissolved, and only the solid that wouldn't dissolve will come out on the filter paper, okay? But again, be careful using it, okay? Make sure that you actually really need it. So check with your instructor before you do a hot filtration, all right? Another thing we consider with the recrystallization when we're choosing our solvents, we are looking at things that are like the compound that you want to dissolve, okay? So we want to dissolve a carboxylic acid. We're using ethanol for that, and then a little bit of water, because the carboxylic acid's a fairly polar compound. Ethanol and water is a fairly polar compound. Our neutral compound is not as polar, but with the little hexane that might be remaining, and then the ethanol, that will help crystallize out your neutral compound, okay? Without adding, we're not going to add water to it, okay? So this table, figure 1.4 from your lab manual, shows you the relative polarity of some solvents and some common solvents that we use, especially for recrystallization, and how they would compare for different types of compounds, like ionic compounds, hydrogen bonding compounds, things like that. Okay? So, with the recrystallization then, you're going to, with the carboxylic acid, after you've added the ethanol to get it dissolved, and remember we want to be careful not to use more than 10 milliliters, then you're going to add, and this needs to be hot water. So it has been in a container on your hot plate getting hot until the solution gets cloudy and stays cloudy. And this doesn't mean gets everything to crash out. Just it should be clear, transparent, gets a little cloudy and stays cloudy. And what you have to be careful of, is it cloudy or is it just the two solvents mixing? Just the two solvents mixing isn't going to count as cloudy. Or until you've added the same volume of water has been added. As the amount of ethanol added. So you don't want to add more water than ethanol that you've added, all right? And when you add the water, it may not become, even if you've added the same amount of water as ethanol, it may not become cloudy, but you're not going to add more water than that, okay? You're just going to, once you have gotten everything dissolved, you've added the water, you're just going to set aside your carboxylic acid and let the crystals grow and move on to the next step, okay? Because the best way to form those crystals is for everything to sit still so that the crystals can form. If you keep jostling the flask that you're trying to grow crystals in, you're not going to get really good crystal formation, okay? So we're going to set it aside, let it cool to room temperature. Once it's cooled to room temperature, we can set it in an ice bath, but remember, keep the flask clamped. We don't want any more water in it, okay? Or we don't want your solid floating in the ice bath. So when you set it in the ice bath, make sure it's clamped, let it cool 15-20 minutes, or 10-15 minutes, and then you're going to filter it, okay? Filter it and recover your carboxylic acid crystals that you have, all right? For the hexane, make sure that we have our neutral compound. Before we get to recrystallization, what we need to do is what is called a simple distillation. And this is for the neutral compound. And with a distillation, this is a way to purify or to separate components. Your separation is based, the separation will work if there's a difference in boiling points. And you need, for a simple distillation, for that type of distillation, you need a fairly good difference in boiling points, okay? So think about the hexane, if you can remember from putting your pre-lab together about how much hexane, or what is the boiling point of the hexane, okay? It's going to be lower. Does anyone recall offhand? No memories? Okay.
69.
Right, 69, so 60s to 70s. It's going to be fairly low, okay, as far as boiling points go for things in organic chemicals. Your neutral compound is either going to melt at 54 degrees or 80 degrees, okay? So that's just its melting point. That's not its boiling point. Its boiling point is going to be much greater than that. So that's why we can separate the hexane from the neutral compound, because we've got this big difference in boiling points, okay? Now let me show you the setup for the simple distillation. We're going to have you guys set these up, and we'll show you how to set them up in lab this week, and then we'll check what you have done when you set them up. And then we'll talk about some things to watch out with a simple distillation, okay? So very first thing, when you are setting up a simple distillation, first of all, decide what your heat is going to be, okay? What is your heat source? So we're going to use our hot plate. We're also going to use it to stir, okay? So it's going to heat and stir for us. And then we're going to have our pan of hot water here, okay? We don't need to start with hot water there. We can always add the hot water to it, okay? So the first thing we're going to do is, this is our distilling flask. This is the flask that last week, the round bottom flask that you put your hexane and neutral compound in. That is now your distilling flask, all right? Clamp that guy really well, okay? We don't want to lose what's in there. And this is also the start of our building our distillation apparatus. So we start by clamping that really well. You want to make sure there's a stir bar in here as well, okay? Then you're going to add your three-way, so all those pieces when you checked into lab last week that you had to figure out on the pink sheet what they were, we're going to get to use a lot of those pieces this week with the simple distillation. So one of those is the three-way adapter. You want to get that, so this is nice and vertical, okay? So when you look at things, if they're not nice and vertical, if they're tipped one way or the other, align the clamp on your distilling flask so you get things nice and vertical, okay? Then we'll take our thermometer adapter and our thermometer out of our common equipment drawer. So remember, it goes back in the common equipment drawer, okay? If you don't put it back, then the group that's in it lab after you won't be able to find their stuff, and the lab prof will leave you a nasty pink note in your drawer, okay? So thermometer adapter, go back in the common equipment drawer. You're going to adjust the thermometer to the tip just below this neck of the three-way adapter. The reason is right before it goes up this neck and comes down the condenser, that is the hottest temperature the vapor reached. And so that's basically the boiling point of that vapor that you are collecting, okay? So we want to be able to collect that temperature. So make sure you've got the tip in the right place. Then we're going to go down to our condenser. We're going to put we're going to put a clamp here, but it doesn't have to be super tight. It's just supporting the weight of that condenser, because then we're going to put water running through it, okay? Then we'll have our vacuum adapter that comes down, and then we'll have another clamp to our collection flask. I would put a T-clip between the vacuum adapter and your collection flask, so those are those blue clips in your lab drawer, and a T-clip between your three-way adapter and your condenser, okay? The other thing you can do is you can put a rubber band between these two and a rubber band between these two, all right? The way a condenser works is the water goes in the bottom, okay? So to fill the condenser, we have to fight gravity. If we try and fill it from the top, it's only going to half fill, okay? So water goes in from the sink. We're going to use hoses connected in from the bottom, out from the top. So since you're connecting something to the sink, make sure your apparatus is like near the sink. Don't set it up like on the far end of the hood away from your sink. Set it up close to the sink. And then we're going to, part of when we help check your setup, we're going to check and make sure that water goes through okay. We don't have hoses that pop off. We don't want any splintered hoses, things like that. We don't want to give you a bath or your hood made a bath. And usually, unfortunately, the way these things work is when the hose pops off, it's usually for whatever reason, it's the hood mate that gets the worst of it, not the person itself. So we want to protect your hood mate, but make sure the hose is on tight on both sides so they won't pop off. And then make sure your water out is going to reach it to the drain, okay? So you don't want it kind of just sitting on the side of the sink and then flooding the hood as well. Make sure it goes down in the drain. To get the pan of hot water, make sure you're using hot water from the tap too. That'll save you time. And then also make sure you know what you're going to be looking for in this distillation, okay? We're boiling the hexane, so you're boiling something on the distillation side. You're making the vapor, collecting that temperature, and then you're collecting that vapor over in the collecting flask, okay? So which one is going to have what we want in the end? The distillation flask or the collection flask? Distillation flask, right? Because we want to keep the neutral that's going to stay in here. We're going to get rid of the hexane, all right? So what's always a good idea is kind of measure the volume. Know roughly what that volume is, then you know if you've collected enough. If you know that for sure you added like 20 mils of hexane last week and when you collect it you only get 5, you're probably not done with the distillation, okay? We want to push off as much of that hexane as possible, okay? Otherwise your neutral is so soluble in the hexane, it's going to want to stay in the hexane and not crash out for you, okay? So push that hexane off. We're going to use hot water. We're going to adjust the heat so we get hot enough water to get that hexane boiling, vaporizing, condensing down. And then once you've seen the last of it condensing, turn that water up a little bit more and make sure you push that distillation, all right? Then what you're going to do after you do the simple distillation is you're going to recrystallize with ethanol. So you're going to add ethanol directly to your distillation flask. You're going to keep the contents warm so things stay dissolved. Add the ethanol directly to that and then let that slowly cool down to room temperature, and then you'll cool it in an ice bath and filter it, okay? So you're going to cool everything down in both cases to room temperature, then cool in an ice bath, then you use your vacuum filtration for both solids to filter them, okay? And then label your solids, okay? Because you're going to end up hopefully with 2 white solids and you got to keep track of them. Not only that you know who's who, but also your identifying information is on them. Then we're going to let them air dry in your drawer. Get all the rest of the vapors off from the ethanol and, in the acid's case, the water, and then you'll be able to collect weights and melting points, okay? So the melting points, I want to show you what we're looking for with the melting points, and then give you some examples for the mixed melting points, okay? So for collecting the melting points, first of all, you want a range. You don't just want a temperature, okay? So it should melt over a range. You want a short range, but you want a range. And in lab, we've got multiple apparatus to collect them, okay? So first of all, let's look at what we're looking for with the melting point. You're going to look with the melt temps, the apparatus that you will use to collect the melting point ranges. You're going to look in this magnifying glass where your capillary is with your solid in it. And we're going to show you how to fill those capillaries in lab this week. We'll also show you these melt temps in lab this week. You get your solid in your capillary. You start, things start heating, and you notice the first drop of that solid melting, okay? Then over the course of a temperature range, you're going to get it to where the last drop melts, all right? That is the range you report, is from when the first drop melts to when the last of it melts. So here from 120.4 to 121 degrees Celsius, 121.0, that's when that solid melted, all right? So you want to record the range, okay? Make sure it is a range, and then the other thing you're looking for is in the end, for our good narrow range melting point ranges that we're collecting, we want a narrow range. You don't want a really broad range, okay? So be careful when you're collecting these. Either you're collecting it too quickly and that's why it's broad, or if you're collecting it really slow and it's still really broad, either it's impure or it's not completely dry yet, okay? So just be aware of what's going on. But with the melt temps, we've got 2 different types, like I said. We've got this type that either has a case over this or just like this, where we're going to put our samples in here. We're going to look at the sample, and you've got a lamp here, so just be careful. You're going to look through this hole, and you've got a lamp here. Don't burn your nose on the lamp. And then you've got a digital thermometer that you're looking at for recording the range. it turns on here, and then the thermometer you're going to have to turn on, and then there's going to be a dial that you control the voltage with. That's how fast it heats or not. Okay, so in a little bit I'm going to talk to you about heating up things quickly or not. That's what I'm talking about with these type of melt temps. With the other type of melt temps that are in 3109, so those type of melt temps are in 3129, and then the adjacent instrument room off 3129. The other melt temps kind of look a little similar to that, but they don't have a thermometer sticking out. They are, you can program in where you want to start heating, what temperature you want to start heating, and how fast you want things to start heating. Okay, so you're not messing with a dial, you're programming things in. This set of instructions is by each of the melt temps. So the first time you go to use it, just read the instructions for that. Okay. Now with the possible compounds that we have, we need to figure out between all of these 7 acids, first of all, which of them is our carboxylic acid. And a lot of these melting point ranges are pretty close together. So just taking a melting point range is not going to necessarily tell us what we need to know, okay? We'll need a mixed melting point. So in a minute here, I'll talk about that. With a neutral compound, you should be able to figure out what that melting point, what that compound is based on a slow melting point range, okay? So first of all, for just the melting point ranges of either carboxylic acid or the neutral compound, I recommend you taking a fast range. So that's about 5 to 10 degrees heat climbing per minute. That helps you get the ballpark of the range that you need, okay? Because otherwise, if you wait, you know, our last acid melts at 155 to 157. If you slowly heat up that melt temp and just wait and wait and wait and wait for it to melt, it could take you like an hour or more to just take one melting point range, and you don't want to do that, okay? So get a fast range, okay? Then cool the melt temp about 20 degrees, okay? Then get a slow range, so you haven't had to wait, you've gone fast to find what the range is, and this should be a pretty, it may be a broad range, but you've got the ballpark. Then your, for your slow range, you should increase the temperature 1 to 2 degrees per minute, okay? But then it won't, you know, if you're increasing it 2 degrees per minute and it's about 20 degrees that you've got to go, that's going to take you 10 minutes, okay? So it's a lot faster to do 2 than to go really slow with 1. So neutral compound and the carboxylic acid, you want a fast melting point range and you want a slow melting point range. Neutral compounds you can identify with just these 2, all right? There's enough, the 26 degrees difference is enough to figure out between the 2, okay? Unless something's really not pure, something's not working right, but you should be able to figure them out, okay? With the carboxylic acid, then we need a mixed melting point range, okay? And so what that means is we're going to take about 20 milligrams. So how much is 20 milligrams in grams? 0.02, right? So not 0.2, 0.02 grams of your acid, okay? And you need about 20 milligrams of the known solid, okay? So in lab, we have vials of the carboxylic acids, of the known original carboxylic acid. You're going to take 20 milligrams of that known carboxylic acid, 20 milligrams of your unknown acid. Then you want to crush well and mix well together, okay? So once you crush them together and mix them well together, if they're the same compound, what do you expect you should see as far as the melting point range based on what you collected of just the unknown? You should see about the same range, right? But what if they are different? Do you remember colligative properties from Gen Chem? What happens when you've got, then it would be an impure sample, right? If you've got one thing that's one component, one thing that's something totally different, what should happen to the melting point? Remember what happens when you've got an impure sample? Does it raise or lower? You're going to lower the melting point range, right? If you've got an impure sample, you will lower the melting point range, okay? So if you've chosen the correct thing to mix together, you should see a melting point range that is fairly close to your slow melting point range, all right? And with the mixed melting points, you don't have to get a fast range and a slow range. You already know what ballpark you're looking for, right? So you just need a slow range. If they're not the same thing, then you should see a depression and also a broadening, probably, of the melting point range, all right? When you compare it to what you took originally, okay? So I'm going to go through some examples here. First of all, I've got one sample. We've got a melting point of the unknown is 100.3 to 101.9 degrees. What compound do you, or compounds do you think we should try for mixed melting points? 100 to 101.9. Thoughts? Any of them? What is it closest to? The first one, 2-methoxybenzoic acid, okay? So we use and we get the mixed melting point of it, and that's 99.5 to 101.1 for the mixed melting point. What do you think about the match there? Do you think you found it? Yes. Pretty much. I mean, it's a little bit lower, but you look at the range, it's 1.6 degrees, 1.6 degrees. Maybe just a slight bit lower, but you're really close. That's probably a good match for your mixed melting point, okay? So with the mixed melting point, hopefully is as close as possible to the original melting point range, but it may not be like spot on in the tenths of a degree, okay? So if there's a little bit of variation, that's okay. Now let's look at another one. So we've got a melting point of the unknown 149 to 153. What do you think we should do the mixed melting point with? So we could try the 2-bromobenzoic acid or the 3-chlorobenzoic acid, right? Those are kind of two possibilities there. So let's try the 2-bromo. Now, one thing about this, 149 to 153, is that really great for a slow range? That's 4 degrees. Usually we want, 1 to 2 degrees, okay? So that's kind of broad to begin with. So just keep, think about that as you're collecting these melting points. So we use 2-bromobenzoic acid. And we get 145 to 148 degrees. Is that a good match? We kind of really lowered it quite a bit, right? I mean, there's not even part of it that's in the same range. So this is probably not a good match. So you probably would then want to look at your 3-chlorobenzoic acid, okay? So these are just some examples of what you want to be looking for, okay? But do remember you want weights of your final compounds as well, okay? So we have to let them dry and then we can collect those. We will have some time next week in lab to get weights and to get melting points, but there is open lab this week as well, so listen to suggestions from your prof whether they want you to get started or wait till next week getting those masses and melting points and mixing them. Okay?